Hey kids, Mr. Martin here. I'm just generating this recording, this screencast, so that you can get through this first section of chapter 15. What I've done is written down your homework here, so it's page 656, number 15 through 18. So please read on and read the first 5 sections of the chapter so that we can discuss it when I return. Let's get started. So today we're talking about chemical equilibrium, and I just want to kind of state before we get started that it is a dynamic equilibrium. Like most of the time in equilibrium, like we've talked a bit, like maybe in physics class, you talk about equilibrium, and maybe even in biology, which would be a little more relevant to our world, but it is dynamic. It is not like a still photo, it's moving back and forth. Forward and reverse. You have two reactions, a forward reaction and a reverse reaction. So it is dynamic. It is not just still. So there's two reactions. This is the first one here. This is the forward reaction. I use this example. We're going to use it quite a bit today. But it's N2O4 and it goes to 2NO2. It shows a one direction, but I'm showing you that this is just defining the forward rate, which is this rate constant here, the forward rate constant, times the concentration of N2O4. And this is that disappearing. Here's the reverse. And notice what has happened here is that my 2NO2 is now my reactant. So my reactant's going to products like we normally see it. This is called the reverse reaction. The products and the reactants swap place because it does. It goes back and forth. So this would be the reverse rate, and it is the reverse rate constant times the concentration of NO2 squared because the coefficient 2 becomes the exponent. I'm going to say that several times today just so that you understand. All right, so that's what we have going on. And so here's the second part here of this. Not only do we have a forward and a reverse, but we're going to set them equal to each other. The forward reaction has to be equal to the reverse if we're having a true equilibrium. They're both moving and they have to move at this certain rates or something would get clogged up or something would get overloaded within the reaction. So when we have our rates, we can substitute in our two rates. We have our forward rate constant times this concentration of N2O4 is going to be equal to our reverse rate times the concentration of NO2 squared. So what I want to do is I want to solve for Kf over Kr. And how I'm going to do that first is by dividing out Kr. So when I have this, when I divide out Kr, I get this scenario right here, Kf over Kr, and that's what I'm looking for. So then from there, I just need to take this N2O4, divide it out on both sides, and now we have this set up here. Look, N2O4 cancels out. I have Kf over Kr, but now I have my products squared over my reactants. There it is. Clean it all up. Let me scoot it on up so you can see it. There it is. Products over reactants. Well, we're going to take this Kf over Kr and we're going to make a rate constant. And I'm going to tell you right here, Kf over Kr is going to equal this Kc. This becomes our equilibrium constant. K is our equilibrium constant for the whole reaction. We've combined the forward and the reverse to give us this K. And here's the expression. So it says here Kc, which is our new equilibrium constant, is going to be equal to our products raised to the power of the coefficient over the reactants, again raised to the power of the coefficients. This is our equilibrium expression. That's what we refer to as our expression. So the coefficients become the exponents in our expression. All right, we're going to keep moving on. I have here the second page, and this here says that equilibrium expression relies on stoichiometry, not the mechanism. We just got through with rates and mechanisms from chapter 14, but in 15, where we're relying on equilibrium, it is on the stoichiometry, which is the true equation, the reaction that we see. So we're going to use today as this example as the Haber process. Franz Haber, we've talked a bit about him going through World War I and World War II and his work with gases. Not real nice, but nonetheless, he did give us this here. This is the production of ammonia. So ammonia was developed around the turn of the century in the 20th century. And so through its development, it creates this equilibrium. Nitrogen, hydrogen yields ammonia. But look, it also goes the other way. So if you squeeze on it, adding pressure, it's going to force it to the right, generating some ammonia. And that's what the part of the Haber process is. But it has to maintain some sort of temperature, some constant temperature to maximize production. Excuse me. In doing so, we can isolate ammonia through this process and then put it into fertilizer, and then it increases the food. And that's what happened around the turn of the century with the population boom because of this process. So I wrote here a couple notes. This one here, it says double arrow shows the equilibrium. So anytime you see this double arrow, you know it's an equilibrium, meaning that there's a forward and a reverse reaction going on. The coefficients become the exponents. There's that term again, so I'm going to write the expression. And here it is. Here's the expression for the Haber process. It has the products, which is our ammonia squared, over our reactants. Nitrogen, it has to the first power, understood first power, and hydrogen to the third power. So don't forget those exponents. Cannot stress that enough. Because it is a mathematical operation, we cannot forget it. So it says the concentrations in the expression are at. This should say are at equilibrium. So it means that if you're given initial concentrations, you have to ignore them and develop the equilibrium concentrations. And I'm going to show you how it's related. And then you can plug them in there for the mathematics. All right, so we're going to jump to table 15-1. That's in our textbook. So it sits right here. Right here, here it is. This is on page 626, and it has this table here. And this is for the reaction N2O4 and NO2. And so you can see the start here. There's experiments 1, 2, 3, and 4, and there's these first two columns that are initial concentrations. These first two columns we're not going to use for the equilibrium expression, but they are useful to determine the change in how to develop equilibrium. Here are your two equilibrium columns, and we're going to use these for the expression to develop our K constant over here on the far right. So let me show you what's going on. So back to our notes here, and you'll see that I'm going to use this first experiment, number 1, and here's this reaction, N2O4, and here's the double arrow. It's an equilibrium with 2NO2. Okay, cool. So now, here's this how I have it set up. I might have set up a little bit different. So instead of initial going down, I have it going across here. So these are my initial concentrations for N2O4 and for NO2. Notice I'm not using that exponent here. But this is still valid when I'm referring to these values. Let me show you why. So if I have initially, I don't have any N2O4, but I have 0.02 molar of NO2, and I set this into a container, it's going to automatically start to generate N2O4 because it's in an equilibrium. So this is what's next. This is called the change. That's what delta is referring to. Delta is the change. So on this first one here, it's going to change by 0.00140, and this was going to change by negative 0.0028. Notice that this is half the change as this one here. Because, and you're probably wondering, where'd you get the change from, Mr. Martin? From right here. These are the equilibrium that I stole or took from the chart that was on page 626. And this chart here, it gives me the equilibrium concentrations. And the difference between these two is merely this change here. So this goes up by 0.0014, and this goes down from 0.02 to 0.0172, which is 0.0028. Notice this is twice as much as the change over here because of the 2. That's how it works out. So these two values, 0.0014 and 0.0172, are the two values that I will place in my expression. Let me show you what's happened here. So I've written here my equilibrium expression where I have the products over the reactants, and the products are squared. I don't forget that exponent. And so now I can plug in this 0.0172, and it goes right here. This is my product concentration at equilibrium. This is my reactant concentration at equilibrium right here, and I plug it in, and I get the value 0.211. And you'll notice that you get the same constant just at that one temperature. If we change the temperature, then the constant changes. We learned that from chapter 14. So that's what it does, and that's how it works out. So try this, and so that you can see the relationship between the concentrations and the rate constant. All right, kids, last little bit of information before I let you go. So it says here, if K, the rate constant, is greater than 1, then that means the products are favored. And it is completely mathematical. Remember, your products are in the numerator. So if this is larger, then your K value will be larger than 1. Notice that ours is less than 1 for this particular situation, so then it favors the reactants. Another way they do say it is K is greater than 1, so then it favors the right, or it goes to the right. But if this one here favors the left because it is less than 1, or it favors the reactants. Either way is fine. All right, kids, you should be able to do your homework, and it is a lot of writing out the expression, the equilibrium expression. And I will keep this up there so you can always refer back to the video and take a look if you have any help or anything like that. Please let me know if you have any questions. I hope all is well, and I'll get your message for you tomorrow. Take care.